Now for part 3. In this video, we'll cover surjectivity, injectivity, and bijectivity. First off, referring back to the odd-even function, as it turns out, a non-example of injectivity, which we already know. But what about surjective? Here's the details of a non-example. We know two unique inputs returns the same output, which counts it out as injective. Well, check it out. The codomain is the entire set of even numbers, not including 0, while the range is a set 2, 4, and 6, which is a subset of the codomain. Do you see any red flags? The counterexample, surjectivity, describes a function where every element in the codomain or the potential output set is mapped to by at least one element from the domain or the input set. Essentially, the entire codomain is covered by the function's range or image, meaning there are no unused output values. A surjective function is also known as a surjection or an onto function. Given that, in this example, the restricted range, lowercase r, is a giveaway that our function, well, at least the way it's currently written, is also non-surjective, because the codomain is not entirely covered by the function's range. Here's a question. What's the name of a function that's neither surjective nor injective? As far as we know, there's no name for it. Here's a suggestion. How about nonjective? A function is called surjective, sometimes referred to as onto, if its range is exactly equal to its codomain. So, if we don't define a separate codomain, every function would be surjective by default, rendering the concept meaningless. But like with the domain, if for any reason we can restrict the codomain as the following set of integer even numbers, 2, 4, and 6, rewritten in the blue box. See that? Now the entire codomain is covered by the function's range, meaning there are no unused output values. And a nice thing about this arrangement is the entire inputs do not have to be used. Thus, the way it's written, the odd-even function is now surjective or onto. That being said, we can drop the casual name of odd-even because, depending on how it's written, it could be surjective or nonjective. We can rewrite our function observe, ladies and gentlemen, refers to their previous video. If you've seen it, recall the expression in the blue box. One purpose is to give the reader an impression of the function's potential and behavior. Because if we do away with the restricted domain and range, our function reveals its true potential. Observe, the codomain is capital E. The domain is now unrestricted. Now the function applies the set of natural numbers, which returns the set of even numbers. It's not shown here, but we want to make it clear. The range of the function includes only positive even numbers greater than 0, because a negative number such as -2 or 4 and so on are considered even numbers. Since the codomain is now entirely covered by the range, we have a surjective function, but it still counts it out as an injective function because two unique inputs still give the same output. But we can't live in a world of non-examples. Something has to give.
You know, gentlemen, when you think about it, neither one of you would have a job without the other. I mean, what would a critic do without actors to criticize? And Mr. Makovsky, who would ever have heard of you if it wasn't for the critics?
Alas, the injective function. Check out the white box. We have f of x equals 2 times x, which could be very familiar because it's the standard formula that returns even numbers. It also could be written as 2 times k. provided the inputs are integers, which could be negative or positive. However, the blue box writes it as f, which maps the natural numbers to the natural numbers. For a change, we'll count 0 in the natural numbers. The red box, x is greater or equal to 0, because 0 is considered an even number because it meets the definition, which is an integer that is divisible by 2 without a remainder, where it can be expressed in number 1 as the form 2k, where k is any integer, then setting it equal to 0. Upon solving for k, divide each side by 2, returns k equals 0. Whereas, if we do the same with the standard formula for odd numbers, expressed in number 2 as 2k plus 1, where k is any integer, then setting it equal to 0, upon solving for k, subtract 1 from both sides, divide each side by 2, returns k equals negative 1/2. Since 2 does not divide 0 without a remainder, we cannot find any integer k such that it solves the formula 2k plus 1 equals 0, because we know fractions, which are decimal numbers, are not integers. Therefore, the number 0, by definition, can only be even. Then, the domain of natural numbers is the entire shaded region. The codomain of natural numbers is also the entire shaded region on the right, but the range is the entire set of even numbers, which counts it out as surjective, because the codomain is not entirely covered by the range. However, unlike for our nonjective function, no two different input values produces the same output value. Accordingly, since each input maps to a single distinct output, this counts it as a function. With a further condition, each output is produced by a single distinct input, which means every output in the function's range is associated with exactly one input, which is contrary to the nonjective function, where each output in the function's range is associated with two inputs. Both are satisfied. Thus, it's finally counted as an injective function. Very nice. Conversely, another way of considering it, if two inputs produce the same output, then we can deduce those inputs must actually be the same. Hold that thought, because we'll refer back to that when we do proofs of injective functions coming up. Here's something that's interesting though. The way it's written, it's impossible for the function to return odd numbers. So why is the codomain the set of natural numbers? Because just consider, a function's codomain is the set of all possible values the outputs are constrained to fall into, as it represents the target set where all potential outputs must reside, ensuring that the function produces results within a defined scope, even if not all the values in the codomain are actually attained by the function's output. That all works. However, for this function, we have where the codomain is showing the function's potential, albeit it's not obvious or explicit, because if we times 2 with the number 3.5, returns the number 7, an odd and natural number. Although it's not incorrect to write it as it is, could we rewrite it so the function shows its full potential? For example, observe the blue box. Now we have the function f, where r maps to r, which is articulating the real numbers maps to the real numbers. It's not shown here, but we want to make it clear. Again, the range of the function includes only positive even numbers. Then the domain is the shaded region, but then we can restrict it as the natural numbers. It follows the codomain is also the shaded region, the real numbers, but then we can also restrict the range. The lowercase r, the set of even numbers, which still counts it as injective and non-surjective. See that? But strangely enough, for us anyway, a tiny edit puts 2x in a better light to see its potential. What do you think? But what if we have 2x where r maps to r, but we do not include the restrictions? This would mean the domain and codomain are both the set of real numbers, capital R, which means the codomain is covered by the range. Since the function 2x from r to r is both one-to-one and onto, it's called a bijection. It represents what is known as a one-to-one correspondence between all real numbers. This is because it's both injective and surjective. Essentially, a bijection is a perfect pairing, ensuring that for every element in set X, there's a unique corresponding element in set Y and vice versa. One last example. If we rewrite the blue box where n maps to E, the set of even numbers, again, the range of the function includes only positive even numbers because 2x is injective, and since its entire codomain is covered by the range, it's also surjective, which also makes it a bijective function. To be clear, a one-to-one function and a one-to-one correspondence are not the same. A one-to-one function is injective. A one-to-one correspondence is a function that is both one-to-one and onto, which means it's bijective.